I hope you all have been doing well. I wanted to I'm going to ask you all, see how you're all doing with the material up to this point. But first, I wanted to mention something about the WebAssign, since it seems a lot of people had trouble with multiple ways we can think about how to calculate IQR. So there's this idea of inclusive versus exclusive reasoning whenever you're thinking about how to calculate quartiles. And in the case of WebAssign, and in the case of what we're often going to be doing in this class, we want to think about inclusive reasoning. So look at these 5 numbers. The median is pretty obvious, it's 3. But what I want to propose is if you wanted to ask what the third quartile is, well, there are 2 different ways of thinking about it. An exclusive reasoning means you would think about it as halfway between 4 and 7. And inclusive reasoning means you would think about it as 4. And the nuance here is, do you include the median when you think about it? Is the third quartile the median of these 3 values? Or is it the median of these 2 values? And the latter is exclusive and the former is inclusive. And I believe WebAssign wanted you to do inclusive and say 4 was the third quartile. So in the future, if you're doing a WebAssign, use inclusive reasoning. That being said, I'm not explicitly planning on having you calculate IQR outside of Excel for the remainder of this class. So the nuance here is it really only comes into play when we're dealing with really small data sets of discrete numbers. And I hope that you never really have to do something like that in the real world. We should be more interested in larger sample size and general numeric values, in which case you should probably just use the software in Excel to do this calculation for you. Any questions about this? All right. I'm sorry that caused us a lot of confusion. Hopefully we can move past it. So I'm going to talk a bit about box plots today, and then I'm going to do a lot on the normal distribution. But before I do, are there any questions up until this point on content?
I had a question.
All right.
I was wondering, I guess, I don't know if we went over it and I was just stupid, not paying attention, but would we be able to go over what, like, exactly a standard deviation is? Like, what it, like, as a concept, like, what?
As a concept? Well, it's an interesting question. I guess you can think of standard deviation as an average of deviations from the mean, which I say that loosely because that's the idea, but that's not actually the explicit computation. So if I had a normal distribution, or maybe I should be even a little bit more simple. So I observed a bunch of data and I got a histogram. Something along the lines of this, right? And in my histogram, my mean here, my X bar, is right here smack in the center, okay? Standard deviation is an expression of how, I guess, spread out all of the values other than the mean are. Because think, if we had values that were really spread out and values that were really together, they could have the same mean, but we want to have a way of expressing this sort of difference. And standard deviation, what it says is, okay, so we have a bunch of X values here, we have a bunch of X values here and here, et cetera, et cetera. And what it says is, for every single X value you have, calculate how far away it is from the mean and square it. Then add them up and divide by n minus 1. So think of actually just this part. It's like we're scoring every single value, where values that are really far away from the mean get a big score, right? This is very big if xi is very far away from the mean. Mm-hmm. And values that are very close to the mean get a small score. Again, this is very small when each x value is very close to x bar. So the idea is we're sort of like scoring every value in our data set based on how squished into the mean they are, and then we're averaging those values. So I guess the intuition here is that this number, this standard deviation calculation, it should be pretty big if all of our x values are really far apart from one another, if they're all away from the mean. And it should be kind of small if they're all close to the mean. So the standard deviation is just a way for us to describe numerically this idea of like fat versus skinny distributions.
Okay.
All right, are we still wrapping our mind around it?
I think so. And then like I Googled it, and there's like from what I understand, there's like I got like percentages of like 34, and then like something else, and
So actually that is so not 34%, but we are going to talk a little bit about area under the curve within a standard deviation from the mean.
okay.
That's coming up. Don't think about it as an area under the curve kind of thing quite yet. Right now we're just thinking of it as a number that represents how fat or skinny our distribution.
Okay.
All right,
Thank
I'm
you.
ready to say short or tall our distribution is. All right, no, these are actually questions. Anything else before I move in? All right. So the first thing I want to talk about is conventions for outliers. And we had, I believe in the lecture video, we had this example of tornadoes in Oklahoma. And I said, and granted I made up these numbers, so don't check me on this. I said over the last couple of years, last few years, we saw these numbers of tornadoes. And this is me ordering all of those numbers. And I said, maybe in the year 2020, there was a large amount of tornadoes, a huge amount, in fact, 25. And I think I may have even referred to this number 25 as an outlier because it's so big, it's so much different than the rest of the data. I want us to actually come up with a rule to explicitly say whether or not a value is an outlier. So what if instead of 25 we had 10? Like 10 might be an outlier, but maybe it's not quite an outlier. I don't know. Well, let's find out. So in the case of this data, the mean, we start by sort of looking at our usual breakout. So the median is, it's right in between them, my bad. The median is right here in between these two fours. So the median is 4. I believe, using our inclusive reasoning, that this 3 is going to be the first quartile, and this 6 is going to be the third quartile. And then, of course, this is the max, and this is the min. Okay? So, by convention, we call an observation X an outlier when X is either greater than or equal to the third quartile plus 1.5 times the IQR, or X is less than or equal to the first quartile minus 1.5 times the IQR. So let's do it with our example. What is our IQR here? It is the third quartile minus the first, which is 6 minus 3, and it's 3. That means that 1.5 times the IQR is just 3 times 1.5, which is 4.5. So we would classify X as an outlier when it's greater than or equal to the third quartile, or 6, plus 1.5 times the IQR, which is 4.5, which is equal to 10.5. Or when X is less than or equal to the first quartile, which is 3, minus 1.5 times the IQR, which is just 4.5, and this is going to leave us with negative 1.5. All right, so we were correct. I was correct in my assumption that 25 is an outlier. It is indeed greater than 10.5. And my previous question, is 10 an outlier? Well, 10 wouldn't be an outlier because it is actually less than 10.5, so it is within the range of things that we wouldn't consider outliers. So once you've done all this, we can visualize these ideas, this Q1, median, Q3, and outliers. We can visualize them using something called a box plot, which is actually something I erroneously already had you calculate in Excel. So I think I want to do, okay, 2, 3, 6, 7, 25. So note this little blip I've made. This basically means a discontinuity in our number line. And basically it's me being lazy because I don't want to write all the numbers up to 25. So think of it as me kind of like folding the number line right there. The way we would draw the box plot using the data, our tornado data, is we would put, let's see, a line right here. And then a line at 3, right? Yeah. Then one at 4. And one at 6. 7. Dot there. That. Like so. So this is a visualization of the spread of our data. Actually, just like the histogram. And it allows us to quickly visualize where the median is. It's right here, the center line of the box plot, where the third and the first quartiles are. It gives us an idea of what the length of the IQR is. And it actually classifies whether or not a point is an outlier. Because if a point is not included in the box and whiskers, we write it as a point outside of it, and that is specifically where outliers occur. All right, so that is a visualization of our data. And I think I'm next going to talk a little bit about the normal. All right, so shifting gears a little bit. Let's go back to our normal distribution. Oh my goodness. Okay, yeah. And to start out this conversation, I want to mention there is one more way for us to talk about shape, the shape of a distribution. Recall last class we talked about left and right skewed and symmetric. I also want to give us an idea of how many modes we have. So in this example right here, we'll do it like this. We would call this first one unimodal. And basically what is that root's referring to is that it kind of has one bump, right? We're not talking about skewness, we're talking about how many peaks does it have. And in this case, we have one. In this case, we would call it bimodal, since there seem to be two peaks. And in this case, you could argue, I think, or at least I think, that there are actually kind of like three peaks here, but we wouldn't go to trimodal. Above bimodal, we'll just call this multimodal. And we've seen the example already of when there aren't really any peaks. Oh my goodness. Which is this picture. And we call this one uniform. So this is another way to describe shape. And the reason I'm having us do this, here, I'll leave that up, is because I want to talk about what the normal distribution is. It is clearly symmetric. It looks like this, first of all. And it is a symmetric distribution, which means we could fold it on its center and it should line up. It is, as we just learned, it is a unimodal. It should only have one peak. And it is bell-shaped. Now, recall that I believe we spoke about before that the normal distribution is centered at the average of our variable. So if I observed lengths of octopus tentacles, sure, that were, I don't know, 14 inches on average. And I wanted to model this distribution with a normal curve. I would go up here, I would say, okay, these are my octopus tentacles. And they are centered at 14 inches, right? So the normal distribution is centered at the average value. And I think we're about to talk about center of the curve. Okay. So the normal is centered at the average value. We often call this average mu. Right? Which here I'm going to define as the center of a normal. All right? So when I use the number mu and I say it just sort of in general, I'm referring to the point at the center of a normal distribution. We call it mu, just sort of by convention. And I do warn you, there is something else that shows up in statistics that we also call mu. So don't get too upset when that comes. We will handle that. We will handle that when it comes. So the next thing I want to talk about is the normal distribution has two inflection points. And inflection points are specifically the points where the curvature changes. So I hope you all remember from algebra, we had this curve upward, looks like this, a positive curvature. And then we also had a negative curvature. Oh, whoops. That looked like this, right? And the way I always remember them is that the positive one is happy and the negative one is frowning. I don't know, maybe just like my monster yesterday, I might be the only one who actually uses these mnemonics. No, or not mnemonics, these little memory devices. But you'll note I've sort of split apart our normal curve here. And I've specifically split it by the periods in which the curvature is negative, right? That's a curve down, and the curve is positive. These may be harder to see, but these are both curving in a way that we could make a smiley face rather than a frowning face. So we call these inflection points, the points on the curve at which the curvature changes. And the reason I'm bringing these up is because the curvature on the normal curve has a very specific value. I'll do it down here. So on the normal curve, the inflection points happen at 1 standard deviation sigma, and I'm going to get to that in a second, above and below the mean. Which the picture looks like this. So these are the two inflection points here and here, and they occur at the curve at the x values that are within a standard deviation away from the mean. So let me return to our octopus example. I said what? That their average was 14 inches. So it is 14 inches. What if you knew further that they have a standard deviation of 2 inches? Right? So if I were to want to model my octopuses, I would draw something that looks like this, with the center at the average, the 14, right? And I could further say something else. I could say, okay, I think the inflection points happen about here and about here. Well, I know the x values at these inflection points are 1 standard deviation above and below the mean. And since the standard deviation here is 2, that means that the value at this point here is 16 inches. And the value at this point here is 12 inches. Does this make sense? So not only do we know exactly where the mean is with our normal distribution, we also know about where these other points are based on how we draw it. And that's by this rule about inflection points. Example. So, knowing this, what is the average value of this distribution? Can anyone tell me? Approximately.
Isn't it just 68?
68? Yeah, actually, it is. It looks like it's about 68. So the average value occurs at the center of the normal distribution, which in this case is 68. Now, this one's a harder question. Can anyone give me an idea of where the standard deviation is? Or what the standard deviation would be here?
I think just to approximate, the standard deviation could be 4.
4. Okay, so the way we want to look at it is we want to look about where the inflection points are, right? And we know that the inflection points are about 1 standard deviation away. And it looks like between 68 and 72, that is about 4. So you are exactly right, Julian. Good work. So just looking at this normal distribution, we can get an idea of what the mean value is, 68, and what our standard deviation value is, which it looks to be around 4. Very nice. So next thing we want to talk about is, erase this. Next thing we want to talk about is how to start thinking about area underneath the curve. And I'm going to give us a fact. This fact is called the 68, 95, 99.7 rule. And that is, for a normal distribution, we have, excuse me, I've been out of a cold. My voice keeps cracking. 68% of the values are within 1 standard deviation of the mean. 95% of the values are within 2 standard deviations of the mean. And 99.7% of the values are within 3 standard deviations of the mean. So I have a picture of this. And that is right here. So what is this saying? We have a general normal distribution centered at a mean, which our shorthand for the mean here is mu. And these are the x values 1 standard deviation away. These are the x values 2 standard deviations away from the mean. And these are the x values 3 standard deviations away from the mean. And remember, area under the curve corresponds with the proportion of values, right? We scale our density curves just like we scaled our histograms, and we do an area under the curve calculation to get a proportion of values within a certain range. And what I'm saying is, the proportion of values between the range of mu plus sigma and mu minus sigma, so within the range of plus and minus 1 standard deviation from the mean, that proportion is exactly 68% if you're working with a normal distribution. And the same holds true, or I guess something similar holds true, if you look at 2 standard deviations above and below the mean. Then the area under the curve between those two values is 95%. And we do our third thing, which is 3 standard deviations above and below the mean. And 99.7% of the area under the curve is between those two values. So if this doesn't fully make sense to you, I have an example we're going to walk through. But this is the first of the ways I'm introducing to you about how to calculate area under the curve for the normal distribution. Recall, it was really easy to calculate the area under the curve in the case of the uniform because it was just a matter of calculating the area of a box, right? But in the case of our normal, the area isn't that easy to calculate, so we have to use a number of tricks. And this is the first one. It's called the 68, 95, 99.7 rule. All right, so let's practice this a little bit. So if you don't understand it, hopefully this example will kind of illuminate it a little bit for you. Example. 1.4 million people took the SAT in 2008. The scores followed a normal distribution with mean mu equal to 1025 and standard deviation sigma equal to 209. So we can use the 68, 95, 99.7 rule to say 68%, or about 952,000 people scored between it's 816 and 1, 2, 3, 4. So what did I do here? I said we have a normal distribution. So here, I'll even go so far as to draw it. We have a normal distribution that is centered at 1025 and if I go a standard deviation above and below the mean, then the area in between it, which in our case corresponds to the proportion of people that got scores between these two values. But the area in between it is equal to 68%. And written as a sentence, it's this. About 68%, or about 68% of 1.4 million, so 952,000 people scored between these two values. Make sense to us? Okay. Similarly, if we wanted to look at 95% of people, this would be about 1.33 million. We would say they scored between, and I think actually I've written down these numbers and hilariously I think they are wrong. So let me check it real quick. 25 minus So we want to take 1025 minus 2 times the standard deviation, right? So the lower value is 1025 minus 2 times the standard deviation, which is 209, which is equal to 607. And 1025 minus 2 times 209. Oh, plus, excuse me, which is equal to 1443. All right, so about 95% of people scored between these two scores. And then if we want to do the 99%, which it would seem to be about 1.396 million people who took the SAT, scored between, and I'm going to do it quickly for us, so 1025 plus 3 times 209, minus 3 times 209 for the lower cutoff, so they 1.396 million people scored between 398 and 1652. Pretty cool. So if you don't understand this, I would encourage you to sit with it for a little bit and then check your numbers against my numbers and see if we're all coming out to the same thing. But this is the first way that we are going to understand about, the first way we're going to be able to calculate area under the curve probabilities for the normal. All right, any questions on this? Cool. Next topic. Standardizing normal. So, because all normals, or I guess all normal curves, share the same properties. That's symmetric, unimodal, centered at the mean with standard deviations at the standard deviation, inflection points, standard deviation above and below the mean. We can standardize a normal curve, which the shorthand is normal centered at mu with a standard deviation of sigma. That's how you would read this. So we can standardize a normal curve into what we call the standard normal curve. Which we denote N0, 1. So, the idea here is this. So just like we rescaled our histogram, what we're about to talk about is rescaling a normal curve. So if we observed this data right here, so note this is a histogram and we drew a normal curve because it looked like the normal curve really fit our histogram well. Note the only difference really between the two of these is the x-axis. This goes from 7 to 31, and this one goes from -3 to 3, centered at 0. And this curve on the right, if I drew them on the same scale, the curve on the right would correspond to this one, and the curve on the left would correspond to this one. So they're different curves, but they're both still normal curves. This one, however, is a very special one that we call the standard normal. And the standard normal is specifically, in fact, maybe I should write this down. Standard normal is specifically the normal curve centered at 0 with a standard deviation of 1. Okay? So the only thing that really changes from here to here is the x-axis, right? This is our x-axis right here. And whenever you change an x-axis to look like this, we call this new axis the z-axis, which I'm going to talk about in a sec. Actually, I'm going to talk about it right now. So wait, let me do this. Standard normal versus regular normal. So the values of the standard normal are unitless and called z-values. Okay, so this was a lot. What I'm sharing with you now is sort of like a theoretical understanding of this new idea, this normal curve, which is a very specific normal curve. It is a normal curve where mu is 0 and sigma is 1. And what you can do is if you ever have a curve that is just a regular normal curve, so maybe think about our octopus tentacles or any other one, you can take every single x value in this curve, every single one, and you can do a transformation to them, just like we did a transformation with our scaled histogram. So, and if you do that, if you do this transformation to every single x value, the values you have after the transformation will make up a standard normal curve. So, how to do it? Take every x value we have and transform it. And the transformation we want is that the z-score, or the z-value, of any x value that we want to investigate is just that value minus the center point, the mean, mu, divided by the standard deviation of the normal. And we call this calculation a z-score. So this value, if you took any x value that you had and you did this, you minus out the mean and divided by the standard deviation and got this idea of a z-score. The z-score measures the number of standard deviations away from the mean. Oh, excuse me. I want to write this out differently. The number of standard deviations that a data value x is from the mean. So as a small example, And I think I'm just gonna, first time in class, just draw my own normal distribution. If I had a normal distribution centered at mu, and I looked at the point mu plus sigma, so this is the point that is exactly one standard deviation above the mean. Well, if I were to calculate the z-score here, so z equals x minus mu over sigma, well, I'm going to call this my x, right? This is the x value I want to investigate. I want to find its z-score. Well, that would just be mu plus sigma minus mu, plugging in for x over sigma, which is equal to sigma over sigma, which is equal to 1. So note, this point we know is exactly one standard deviation above the mean. And if I were to stick it into my z-score formula, it would spit out 1, which is what I said it was. The z-score is the number of standard deviations away from the mean that a given value is. And of course, this is one standard deviation of the mean, so our z-score came out as 1. So it checks out. Something else to note about our standard normal curve. Is z-scores do have signs. And what that means is when x is larger than the mean, the z-score is positive. And on the flip side, when x is smaller than the mean, the z-score is negative. So in this little example right here, we were looking at an x that was above the mean. We got a z-score that was positive. If we had chosen an x down here to investigate, it would have given us a negative z-score. Something just to know about z-scores. So I have introduced the normal distribution, and I've introduced you this calculation of z-score. If you have an x value, you can calculate a z-score from it. And the reason that I do it why the heck are we doing this? is we can use z-scores to determine the area under the curve. So recall when we were working with our scaled histograms, the area under the curve for a point, or actually, yeah, that way. So the area under a curve was pretty easy. If we wanted to know the area from here downward, all we had to do is calculate the area of the bins. And this corresponded to the proportion of values we observed at and below that point. When it comes to the normal distribution, though, if we want to do that same thing, find the proportion of values that show up at and below this point, this weird curved almost triangle, but definitely not a triangle thing is not something that we could just calculate in the same way we could calculate the area of these bins. This was base times height. This is technically an integral. So the answer is, to do this calculation, we calculate a z-score and plug it into Excel. Cool. And to show you how to do this, I am going to use an example, and I'm going to walk you through how to use Excel and z-scores together to get that area under the curve. So women's heights follow the normal 64.5 inches, 2.5 inches distribution. What percentage / proportion of women are shorter than 67 inches? Okay, so this is a very interesting problem. It is an area under the curve problem, and I will motivate that with our very first step to solving problems like these, which is draw a picture. So we want to know the proportion of people who, proportion of women, I guess women identifying people who have a height less than or equal to 67 inches. So we'll start by drawing our normal curve. It is centered at 64.5 inches, right? And I want to know something about this point, 67 inches. Specifically, I want to know the proportion of people that are shorter than that. And that is going to correspond to an area under the curve calculation less than or equal to this cutoff point of 67. You with me? Just like with our uniform, just like with our histograms, we want to know the proportion of people that show up in a given range. It's an area under the curve calculation. So this is our picture. We want to know this area right here. So step 2 is to calculate your z-score. Which here, we want to know the cutoff 67 or lower. So 67 is our z-score of interest. So we'll call this x. And z-score is equal to x minus mu over sigma, which in this case, our x is 67. Our mu is the center point, 64.5. We are going to divide off the standard deviation, which is given to us as 2.5. And that is actually going to be 2.5 over 2.5 or 1. Okay, so we found our z-score. And the next thing we do, step 3, is go to Excel. All right, I gotta stop sharing. And then I'm gonna share. Ooh, give me one moment. All right, can you all see my screen? Was that a yes? All right, cool. So what you want to do is go into any empty cell in Excel, press that equals to say that you're about to put in an equation, and you want to use the equation norm.s.dist. And norm.s.dist takes 2 values. The first value you want it to take is your z-score of interest. Okay, so I'm going to give it 1. And the second value you need to give it is just 1. Norm.s.dist takes in 2 inputs. The second input is just a true or false value. And for this class, you will always put 1 in as the second input. If you didn't put 1 in, it would actually just give you the value of the normal PDF, which is not something we're really going to be using in this class. So second input is always 1. First input is whatever our z-scored is, which also happened to be 1 in this case. And once you do that, press enter, boom, it'll give you the area under the curve at that point and below. Pretty cool. So according to this, I'm going to stop sharing here and go back. So we use norm equals norm dot s dot dist. In this case, it is 1, 1, and it was equal to 0.841344. I'll round up to 5. Okay, and that's the answer to our question. That's the answer to our question. Apparently, 84.1345% of women are shorter than 67 inches. Pretty cool. Any questions? All right. So my next question for you is, how many women are taller? Well, our first step, of course, would be to draw a picture, but we already kind of have a picture here. And our picture would correspond to the area above this cutoff, right? So our process is mostly the same. We would want to, step 1, draw a picture. Step 2, calculate z-score. And the cutoff here, calculate. The cutoff here is actually the same thing. Now we're looking at everything above 67 instead of things below 67. So again, the z-score is going to end up being equal to 1. The difference, though, is when we go to put it in Excel, Excel only can give the area beneath a point, right? It doesn't give us area above a point. So what we do is recall that the total area beneath the curve is equal to 1, right? So this total area is equal to 1, and we know the area in the blue. So if we wanted the area in the green here, it would just be equal to the total area, which is 1, minus area in blue, which is just equal to 1 minus 0.841345, which I think is approximately 0.158. All right, do we get this? So when you're thinking about upper versus lower tail probabilities, there are always sort of clever ways where you can think about, the total area under the curve is equal to 1, so I can think about complements. I can think about minusing off using 1 and minusing off the area I don't want, which in this case is the area in the blue. believe that is just about all that I wanted to cover for today. So any questions up until now? We are going to have, in the lecture video, I'm going to give a lot of examples of these sort of area under the curve calculations. And I'm going to use some qualities of the normal distribution to show you how you can do, just like how we had the 1 minus area slick trick right here, there are a couple of other interesting tricks we can do with the normal distribution. So, to end today, you all have a quiz. And it's open notes, so I would suggest you to keep these notes open because it should be a pretty simple quiz. It's just to see if you've been paying attention and to see if you came to class. The quiz code is 8 tentacle. And I'm going to go on right now and open it up for us. So please just give me a moment.